It's a great pleasure and great honor to be here to celebrate the two important events. One is Professor Yang's 75th birthday and the 15th anniversary of Yang Mathematical Science Center. I joined the center 10 years ago in 2014. And I have to say that I really feel lucky to have the opportunity to work together with Professor Yang and also have grown together with the center. I'm very proud to be part of it. Okay, with that, I'd like to start my talk. It is based on some recent work together with my student, Zheng Yuandu, Kangyin Liu, and Wenxin Lai. So I will talk about something related to asymptotic symmetry and string worldsheet. So let me start with the motivation. So during the past over more than 20 years, there is some main development in the field of quantum field theory and quantum gravity. That's this so-called holographic duality. It relates quantum theory of gravity in higher dimensions and quantum field theory without gravity in a lower dimensional space-time. In the literature and in the community, there are two main approaches in doing this duality. One is the so-called top-down approach, where we usually start from some well-defined UV complete theory of gravity. For example, we can start from string theory, and from there we can find explicit models and examples of this duality. The famous example actually is also the first example of holographic duality is this type 2B string theory ADS5 times ADS5, and this is conjectured to be equivalent to be a four-dimensional conformal field theory. And there are also a three-dimensional version of that, type 2B string theory on this ADS3 together with some seven-dimensional internal manifold. And this is holographic due to a two-dimensional conformal field theory. There are, of course, there are lots of other examples which you can really construct from string theory, and this is the side of gravity. And you can also, in principle, define the theory of the quantum field theory, and where for both sides of the duality, you can do real calculations and you can do many checks and see, okay, whether the duality is right or wrong. On the other hand, there's also this bottom-up approach, where you just you see, okay, I assume such a duality exists, and then I ask myself, I don't really know what the UV complete theory is. What I know at the moment is that we live in four-dimensional space-time, and Einstein gravity is a working theory of gravity at the classical level. And with this minimal setup, what can I know about the duality? What universal properties I can explore from this basic setup? And there are many examples using this idea. One is this bottom-up approach of this ADS3 CFT correspondence. And recently, there is also an attempt to study flat holography and under the name of celestial holography. And in the studies of this bottom-up approach, asymptotic symmetries played crucial rule, and it is very useful in setting up the duality. And the question I would like to ask today is how can we discuss asymptotic symmetry in this string theory? How do we understand asymptotic symmetry in this top-down approach of doing holography? And if we know that, potentially, we will be able to build a holography in a more controlled way, and it will potentially help us to find these explicit examples of holographic duality in string theory. So in the following, I will first explain what asymptotic symmetries have been discussed in gravity or supergravity, and then I will propose how to study asymptotic symmetries on the string worldsheet. I will mainly focus on the example where the box spacetime is three-dimensional under the theta spacetime, and if time permits, I will also mention two other examples. One is this three-dimensional being called flat gravity, and the other is this so-called TST-TT bar correspondence. So let's start with the first question. What are asymptotic symmetries in a theory of gravity? We know symmetries are closely related to conserved quantities. According to Nutter, once you have a continuous global symmetry, then you will be able to define a conserved charge, the Nutter charge. And this Nutter charge will generate this symmetry transformation either by a boson bracket in the classical theory or Dirac brackets when there are some constraints, or where commutator when we are considering a quantum theory. So the simplest example is the time translation. We know that if the theory is invariant under time translation, we know that we can write down the Hamiltonian. The Hamiltonian generates the time flow, and we have energy conservation. But these are all stories of quantum field theory or even classical field theory without gravity. What happens with gravity? We know that the classical theory of gravity is general relativity. It has general covariance. And if you again ask about the question, what is energy in a theory of gravity, then you will encounter the difficulty. Time translation is just the reparametrized time, right? This is part of this general covariance, and this is usually regarded as a gauge redundancy. And how can you, it is no longer a global symmetry. How can you use this to define energy? Well, is the development we keep asking related questions lead to this development of this so-called asymptotic symmetries. For example, in the 60s, this people found this BMS group for flat Einstein gravity in asymptotically flat space-time. And the main idea is as follows. The question or the tension regarding defining the conserved quantity and the time translation being a diffeomorphism really boils down to the question of boundary conditions. A theory of gravity is actually defined not only by the action, but also by a choice of the boundary conditions. Once you choose your boundary condition, then not all the diffeomorphisms are allowed. Not all of them will preserve the boundary condition. Only those ones that preserve your choice of boundary condition are the allowed transformations. Of course, there are transformations that are very local. They only happen in the middle of the space-time and will have no effect at infinity or the boundary. Then such transformations will still be gauge redundancy, and these are called trivial symmetry transformations. So this asymptotic symmetry group is given by all the allowed symmetry transformations. In the case of pure gravity, it's the diffeomorphisms that preserve the boundary conditions that you choose, marked by the trivial ones for very fast near the boundary. So of course, it is when you say it depends on the boundary condition, then usually you need to be clever. You have to choose a clever set of boundary conditions, and after the whole procedure, all these charges you find should be finite and conserved and integrable, and this action of the asymptotic symmetry group has to be well defined. And examples of this, as I mentioned, contains this discovery of the BMS group in four-dimensional Einstein gravity, and this two-Virasoro algebra for asymptotically ADS3 spacetime. Let me focus on this story of ADS3. So ADS3 is the solution of Einstein gravity with a negative cosmological constant in 3 dimensions. And here I give an example of ADS3 spacetime. And the coordinates are phi, u, and v, where here u, v are two Lagrange coordinates, and phi is a radial direction. And when I take phi to be very large, it denotes the asymptotic boundary of this non-compact space-time. And the metric has local asymmetry. It has 6 generators. It's SL2 cross SL2. And this is about this particular solution. When we talk about this, the solution, the boundary condition of the theory, usually we are talking about a class of solutions to the Einstein's equation. And usually we can take this so-called Feynman-Graham expansion. So this phi, the radial coordinate is here, and then this all the other directions we can expand the metric component in terms of powers of e to the minus 2 phi, and then when phi goes to infinity, it will require this class of solutions to be the same as this ADS solution that explicitly right here. And this is this Brown-Hanot boundary conditions. That is to say, the class of solutions the or differ from this particular one I gave by order one correction, at most order one correction, or metric that has this behavior are allowed in the solution space of this Einstein gravity and under this Brown-Hanot boundary condition. Then we can define the notion of asymptotic Killing vector. And asymptotic Killing vector is unlike the exact Killing vector is defined by the condition that the Lie derivative on the metric equal to 0. But asymptotic Killing vector satisfy this the condition that this Lie derivative on the metric is not 0, but is order 1, the same as required by the boundary condition. And if you require that, then you can just solve this asymptotic Killing equation and find all these possible asymptotic Killing vectors. And it turns out that for this theory, for Einstein gravity in 3D, with this boundary condition, you'll find that the asymptotic Killing vectors are generated by the left-moving and right-moving Virasoro algebra. So these are the asymptotic Killing vectors. And this, according to another theorem, once we have some symmetry, we can try to define conserved quantities. For each of these asymptotic Killing vector, we can also define a conserved charge. And these charges can form an algebra. In this theory, these charges, they form a Virasoro algebra with a central charge that is given by 3L over 2G, where L is the length of ADS and G is a three-dimensional Newton's constant. So this is the story of finding asymptotic symmetry for ADS for asymptotic ADS3 spacetime in Einstein gravity. And this is very helpful. In principle, you can, with this piece of information, you already know lots of things. Because you find this asymptotic symmetry algebra of this gravity under this boundary condition. And this asymptotic symmetry is given by left-moving and right-moving Virasoro algebra. And this is precisely the same as a two-dimensional conformal field theory. And by this, you know that the phase space of Einstein gravity is organized by this asymptotic symmetry, and hence it's the same phase space as that of this 2D conformal field theory. And furthermore, you can study black holes in this theory and find that indeed this entropy in Einstein gravity can be reproduced by this entropy formula from that of 2D conformal field theory. So this is all from this bottom-up approach without using string theory. Now, how do we see this asymptotic symmetry in string theory? Okay, this is the question we want to answer. And so there's the proposal. So let's consider the worldsheet theory for on a target spacetime with metric G and possibly B field, NS field B. And we know that space-time, exact symmetries of space-time correspond to global symmetry on the string worldsheet. And this symmetry generator on the string worldsheet is just another charge in a two-dimensional quantum field theory. And we know that string equation motions and Virasoro constraints are all invariant under this exact symmetries. And this and the basically the string spectrum is determined by the equation motion and the Virasoro constraints. This is about exact symmetries on the string worldsheet. Now, the proposal we have is that for asymptotic symmetries on the string worldsheet, the requirement and the properties are very similar to the exact symmetries. We just need to replace the requirement that the equation motion is preserved. In the case of exact symmetry, equation motion has to be preserved exactly. But in the case of asymptotic symmetry, worldsheet equation motion should be preserved asymptotically. And so should we impose this condition to the Virasoro constraints? So by something is preserved or satisfied asymptotically, what do we mean? We mean that if this target space-time of string theory has a parameter or has a coordinate, when the boundary is taken by, for example, by sending phi going to infinity, then by equation motion is preserved asymptotically. I mean, this equation motion equals to 0. Instead of requiring it to be 0, we need to impose that the left-hand side of the equation motion equals to to certain powers of e to the minus 5 or something like that. This the precise form precise requirement depend on the boundary condition you are using. And by this simple and straightforward procedure, we will learn that this asymptotic symmetry in the target space-time of string theory can be realized by some asymptotic global symmetry on the string worldsheet. And for each of these asymptotic killing vector derived this way, there is an asymptotic another charge on the worldsheet. And similarly, physical states will be organized by this symmetry group. And I'll just quickly mention the example of ADS 3 CFT2. To consider that, we need to go back to string theory and consider the worldsheet theory. In order to have a weakly coupled worldsheet description, we want to consider type 2B string theory on ADS3 times some internal manifold supported with some NS-NS3 form flux. And the three-dimensional part of this worldsheet theory is this so-called WZW model. And this is this triangle diagram describes three equivalent descriptions of the same theory. The top is the worldsheet theory, and the left-hand side is the supergravity limit, and the right-hand side is the two-dimensional conformal field theory. Now, this there's some details of the model, and what I want to stress is the following. So we can write down the equation motion of the worldsheet and write down the constraints on the worldsheet. And the requirement is as follows. We consider some diffeomorphism in the target spacetime generated by a vector in the target spacetime, of course. Then this variation of the target space-time coordinate will have to satisfy the equation of motion on the worldsheet in a sense that they fall off the right-hand side is of order e to the minus 2 phi or e to the minus 4 phi. They vanish at the boundary. The boundary is taken at phi goes to infinity. And with these conditions, by some tedious calculation, you'll find that this you can just solve it, and the asymptotic Killing vector is precisely that I mentioned before, that was found by Brown and Hanot many years ago. And you can also write down the worldsheet another charges and find their algebra, and this can all reproduce the result that we did in this supergravity limit. But I want to stress that this is a purely string worldsheet analysis, and we don't need to know the Brown-Hanot asymptotic Killing vector at all. We can just impose such condition on the worldsheet and discover this. And then this is purely string theory analysis, and we can see this asymptotic symmetry really appears there. We can write down the charges. And another example is this of asymptotically flat spacetime in 3 dimensions. As I mentioned before, in the 60s, people found 4-dimensional BMS group there. And here, using string theory, we using the same procedure, we found the 3-dimensional version of that. We found all these super rotations and super translations, and also write down the generators on the worldsheet. And finally, there is another example using string theory. It comes from deforming the first model that I mentioned. So in the string theory set, I perform a so-called TST transformation. T means T-duality, and S means shift, and then T-duality again. After T-duality, I can deform ADS spacetime to some asymptotically flat spacetime with a linear delay tone. And this is really a holographic duality that goes beyond ADS-FT. And the same analysis will lead us to some asymptotic Killing vectors and these charges. We found some very non-local algebra, and it also it is compatible with earlier results. And here is the summary. We asked ourselves a question: what asymptotic symmetries means on the string worldsheet. And we proposed a strategy to find these symmetries. That is to require that the equation motion and constraints to be preserved asymptotically. And it works for this three type of examples. And there are lots of things to be further explored. So far, we have only dealt with bosonic string. It will be interesting to ask about superstring. And for flat space, we did the BMS, we did the three-dimensional version. It is more interesting to find BMS4, which really is related to the real-world gravity. And after all this, we really want to use this asymptotic symmetry to organize the states in gravity theory and to help us to understand more about holography and quantum gravity. With that, I would like to thank all of you, and I'd like to say happy birthday, Professor Yao, and happy 15th anniversary to YMNC. Thank you.
Any question, comments? Yeah. If there's no question, comments, that's thanks.